Okay, so in this video, I want to talk about another class of first order differential equations, which are um, in principle solvable, also eminently applicable. We'll talk about applications in future videos. But here we want to talk about first order linear differential equations. The new word here is linear. Linear differential equations have a very particular structure, which we'll discuss, and that structure is what makes them solvable. We can write down a really concrete method for solving them, and that's what we're going to explore in this video here. So, what is a first order linear differential equation? Well, it's one which can be written in the form y prime plus p of x y is equal to q of x. P and Q here are functions of the independent variable x. And of course, as usual, we're implicitly assuming y is dependent on x. Y is a function of x, in other words. And what we're after here when we write down this equation, when we say we want to solve this, is we want to find all functions y which satisfy this differential equation. Okay? So the way that we're going to do this is through something called the method of integrating factors. The method of integrating factors. And this is a method which will work in principle to solve any first order linear differential equation that we come across. Okay, the idea is that we're going to manipulate the the left hand side of this first order equation here to make it look like the derivative of something. This is all very vague because it's what is it the derivative of? Well, you'll see, okay? This is the idea, this is the inspiration, though, and I want to sort of walk you through the process by which one might arrive at this kind of method rather than just giving you the method without any motivation. Okay, so the idea here is we're going to look at this right-hand side, and what we want, the right-hand side. I'm sorry. I don't know my left and right. Okay, we want the left-hand side to look like the derivative of something. I'll just say look like a derivative. And I'll put dot 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 here. So this is a little ponderous. This is a little bit unclear and vague, and I admit that. But you'll see how this works. So what we're going to do is we're going to we're going to define a new function r of x, which is going to be called the integrating factor. Okay, and I've not defined it yet. I'm just giving it a name. It's going to be called the integrating factor here. So r of x. My cat's going crazy. One sec. Let me pause the recording. Okay, so yeah, like I said, we want to make the left-hand side look like the derivative of something. So what we're going to do is we're going to multiply it by this thing that we're going to call the integrating factor. We're going to multiply it by a function which we're going to call r of x. So we're going to have r of x here, and this is going to be multiplied by this left-hand side here, y prime plus p of x y. And now I'm going to distribute the r of x. So what I end up getting, of course, is r of x y prime plus r of x p of x y. Straightforward distribution, right? And now the point is that we want to make this expression here, this one, we want to think about, is that the derivative of something? Now, I don't know, if you sort of squint your eyes, you can maybe kind of see how this could look like a product rule. This kind of looks like the product rule where you're thinking about the derivative of r times y. So maybe I'll sort of write it as a question mark, like, could this be equal to the derivative d dx of r of x times y? The reason why I say that is because, look, if you take the derivative r of x times y, you're going to use the product rule, like I said. You're going to you could leave the first part alone, take the derivative of the second. That's r of x times y prime. Okay, that takes care of this term. But of course, this term is a little bit weird, right? How could we have the derivative r of x times y be equal to something that looks like this? Well, what we would need, of course, I'll say it like this, to make this work, we need that this r of x, p of x thing, this guy right here, is in fact r prime of x. So could you imagine if we had r prime of x being equal to r of x, p of x? That would be amazing. Wouldn't it be nice if that was the case, right? You all know the Beach Boys, right? You're all proper Americans, properly acculturated to American culture. I mean, I'm not even American, and I know about the Beach Boys, and I love the Beach Boys because maybe more, even more of a patriot than you. My God. Um, don't deport me. Don't deport me. We need this. And wouldn't it be nice if we had this? Because just imagine. Okay, sorry. That was a little distraction. Just imagine that we had r of x times p of x, which is this thing right here. Just imagine that that thing was r prime of x. Then this whole thing here would look exactly like a product rule. This whole thing here would look exactly like the product rule applied to r of x times y. You see that? So can we think of functions which satisfy, can we think of functions r which satisfy this expression here? So what we're saying with this equation is that r prime of x is r of x, it's the derivative of r prime of x is itself, but then multiplied by this other function p of x. Can we think of a function which does this? It's kind of like r prime of x is proportional to r of x, that the derivative is proportional to itself. The derivative of the function is proportional to the function. Like r prime is equal to k times r. Now, this isn't exactly analogous, right? Because k is this function p of x here, but we know what solutions look like there. What we do is we take exp of k times t, right, as our function. Exp of k times t, the exponential function. And indeed, the exponential function is what comes in clutch here. We define the integrating factor to be r of x is equal to the exponential of an antiderivative p of x dx. I'm going to box this because this is something that's always going to work for us. Now understand, what's the derivative of this? So if we have this definition, so then you think to yourself, what is the derivative? What is r prime of x? Well, by the chain rule, the derivative of exp of garbage here is exp of garbage times the derivative of garbage. So this is exp of the integral p of x dx times the derivative of garbage. Can I? I wish I did this differently. Let me. I take advantage of technology here and just move this over. Okay. So r prime of x is equal to exp of the integral p of x dx times the derivative of what's inside the exp. The derivative of what's inside the exp, because this is an antiderivative of p of x, this is, we just multiply by, hello? We multiply by, oh my God, I'm losing my mind here. We multiply by p of x. But look, this first factor right here is r of x. Okay, compare. We said we need this to be true, and look, it is true for this particular choice of r of x. So this is great. This is what's called the integrating factor. And look what happens when we use it. What happens is, going backwards, we see that with this choice of r of x, we have that when we multiply this equation up here, this equation, by this r of x on both sides, of course, you do one thing to one side of an equation, you have to do it to the other, that the left-hand side looks like the derivative of r times y. Okay, so let me write some of this out. So going back to our equation, so we started with y prime plus p of x y equals q of x. I'm going to leave myself a little bit of room because I'm going to write something there. So this is our original equation. And what we're going to do is multiply now by this integrating factor, which is called r of x. We're going to multiply both sides of it by r of x. Okay? And reminder, here's r of x. Don't forget, here it is. It is defined in terms of p of x. It's the exponential of an antiderivative of p of x. Okay? What's the point? The point is that with this choice of r of x, we now get to rewrite the left-hand side as the derivative of r times y. This left-hand side becomes d dx of r times y. And I'm just going to write in shorthand here, r times q on this side. Okay? Now I can integrate both sides. With respect to x. And if I do that, I get r times y is equal to the integral of rq dx. And then to solve for y, I divide both sides by r. In other words, here is my general solution to my first order differential equation. This is the general solution. What am I saying here? Let's just recap. I'm saying that if you have this first order linear differential equation, you can write down the integrating factor. You just read off what p of x is when your differential equation has this particular form. You identify what p of x is. You shove that p of x into this expression for r of x, and that's your integrating factor. Okay? Once you have that integrating factor, you can then immediately leap to writing down the general solution. It's an integral again, but, you're all adults. You can handle that. You have a pair of integrals that you need to think about. But if you can do those pair of integrals, you can then explicitly write down what y is. It's beautiful. Okay? You might worry, oh, no, my professor is so pedantic all the time about dividing by things. What if r is 0? But notice that in the structure of r of x, because it's the exponential of something, it's non-zero, right? The exponential of anything, at least for us and actually for many people, is always non-zero. Exp of anything is non-zero. So there's no harm, no foul in dividing by something which is the exp of something. Okay? All right. That's the method. Now, if there's something that you want to memorize, or if there's something that you want to sort of keep in your memory banks when it comes to first order equations, I would say memorizing the integrating factors worthwhile, and maybe even memorizing the general solution in terms of the integrating factor is worthwhile. These two boxes are worth keeping in your head because they're going to come in clutch when we need to solve problems. In the next video, which will be the last video for this set of videos, I just want to do examples. Okay? All right, see you in the next one.